in Cambridge. I'm blessed to be here the second time. So this is a joint work with Anders Nemeti. And it is about L spaces and L space links. So maybe a reminder definition. So M is the rational homology sphere. It's an L space. If the size of Heegaard Floer homology of M is small as possible, so the rank of the thing is equal to the size of each one of them. And there are many people in the audience who know and love L spaces, so probably I won't say much. Maybe one good thing to remind is this beautiful conjecture of Floer and Watson. Which says that if M is orientable and reducible, and rational homology sphere, and I think that's it.
Oh, we don't really need rational homology sphere.
I
mean, it's just sort of
Because
topologically true.
it's true if it's not a rational.
Yeah. And then M is an L space. You can only if pi 1 of them. So M is not an L space. If pi 1 of them does not. Has left invariant. Ordering, order, whatever. Right, and then there is a theorem of Hanselmann, Rasmussen, and Watson. Which says that the conjecture is still full graph. So, yeah, many people in the audience know this much better than me, so I'm not interested specifically in L spaces, I'm interested in L space links. So what's an L space link? Is that I have a link with several components. S3. And then L is an L space link. If large surgery along the components of L is an L space. And there is a good question how large is large, but sufficiently large. So starting from some point, this should be an L space. And many of you know, so if L has one component, then this is the definition of L space knots, and there are a lot of interesting examples of L space knots. They're used in many examples and counterexamples and low-dimensional topologies these days. So the goal of this talk is to advertise L space links, give some examples, state some properties, and explain what's new about links in comparison to knots. And so how do we check that something is an L space link, first of all? So to check this, there is a useful theorem of Zhu, which says that suppose that, so first of all, we have some L space surgery. Then this is the same is true for all sublinks. For all And then the third condition is some kind of positivity, so I follow the matrix d1 dt on diagonal and the linking numbers of components of diagonal. And so I want this matrix to be positive. So if these three conditions are satisfied, then actually everything after this d1 decay is also null space. So then S3, let's say Q1 decay OL is a null space for Qi, U and I, and so in particular L is a null space. Right? So again, many of you know the thing about L-space nodes, that if you have one positive L-space surgery, then everything after that is an L-space. And it is an L-space node. So here, this positivity condition is replaced by this condition. And also, we need this extra condition for all sublinks. So it looks complicated. The proof is actually very similar to what you would do for one component at some kind of induction. And you go from t to t plus 1 in some direction, and then from exact sequence you see that you need sublink when this component is excluded, and so on and so forth. So that's the theorem, and it looks scary, but actually in many examples it helps, and you can easily check that something is an L-space link. So here are some nice examples. So where do I want to start? Yes, so example number 0. So if I have disjoint union of L-space nodes, Li nodes, then this is an L-space link. That's obvious, basically from the definition, because the surgery will be connected to some surgery. So a more interesting example is the following, which is again due to U. So he wrote a very nice paper when he proved this theorem and gave many interesting examples of L-space links. So in particular, if you have 1-1 surgery on Whitehead link, is the Poincaré theorem. Which is classical fact, and you can draw and check. And so you can use it to prove that Whitehead link is an L-space link. So how do you actually use it? So this is your 1-1 surgery. So lambda will be actually 1, 1, 0, 0, because the linking number is 0. So it is positive definite. Now you have this surgery gives you an L-space. So this is non-trivial L-space. And one surgery on an unknotted component is also an L-space. So you're done. So you can apply the theorem. So this is an L-space. In particular, you can have an L-space link where the linking number of the components is 0, and which looks kind of non-trivial. Another similar example is when you have 1-1-1 surgery on Baromean rings. Is also equal to Poincaré's here. It's another check. And so again, you can write the matrix. It's positive definite. All sublinks are L-space links. And so this is again an L-space link. So you have some interesting behavior. Another generalization of this example is the following theorem of U and Dara, which says that the two-bridge link is an L-space link, two-bridge two-component link, is an L-space link if and only if it is of the form B UK minus 1, minus q, I guess, right? Minus q. Where k and q are positive and negative. So there is an interesting family of two bridge links, which are all L-space links. And so one direction is essentially application of this theorem plus some induction. So you make some surgery and then you relate it to some surgery in smaller k and k. Another direction is due to the Ra, and that's more tricky, so maybe I'll get to this at some point. So you have some restriction on Alexander polynomial for L-space links, and you get it from there, but that's kind of not trivial. Right, so these are 2 and 3 component links. You have some general families with many components. So one thing, the theorem of myself and John Hom, is that if you have k is an L-space node, and I think I want it to be nontrivial, then you can form a cable DM cable. It will be D component link. And this is an L-space link. If and only if M over M, or N over M, how you measure it, is bigger than 2G of K. So for one component, it's actually due to Manhattan, and for more components, we used more or less the same argumentation. So we have a family of cable links this way. And another theorem which is more close to actually the subject of today's talk so this is joint result with Dimitri from a while ago, that all algebraic links are L-space. And if time permits, maybe I'll say in the end why this is actually true, because I'll use similar argument in the end, but yeah. So there are many examples. So these look like very positive links, these look like cable links, but there are some completely non-positive and interesting families like this, the bridge links. There are a lot of things. And so you can ask many questions about them. And one question you can ask, so for torus, for L-space nodes, you know that homology is determined by the Alexander polynomial. So here it's not completely true, but let me say some meta theorem, whatever, is that homology of HF, so link Floer homology of L-space links is almost determined by the Alexander polynomial of the link and all of its sublinks. So we need to know all the linking numbers, and if they're non-zero, we can recover the Alexander polynomial of sublinks. But in general, for L and all sublinks, so if we know all Alexander polynomials for all sublinks, then there is some quite tricky procedure how to reconstruct at least some information about link Floer homology. In many cases it's enough, in some cases it's up to some spectral sequence which we don't know. And that's why we have almost. So almost means that up to some spectral sequences. So actually, I think in all of these cases that I listed, we know the homology exactly. because by various reasons we can compute the spectral sequence and check that sometimes it degenerates, sometimes we can use some symmetry arguments, sometimes we can use something else. So for two components, we know all the information. So with GenHom, we computed it for all cable links and expressed it in terms of homology of K, essentially extended polynomial of K and this K-link coefficient. And for algebraic links, there is explicit procedure how to get it from that extended polynomial.
This is all for integer surgeries, right?
There were no surgeries yet, right? So this is just homology of the link
Okay.
in S3. So for surgeries, yeah, that's another thing to say. Right. And for surgeries, and I don't want to say the answer, so somehow that's not the subject, but I just want to emphasize that we know a lot about these homologies, and in particular, maybe one thing to say is that there was a conjecture by Joan Licada how to compute homology of any torus links. And in particular, corollary from this meta theorem, which I didn't explain, is that so let's see what this implies. The conjecture of Joan Licada about homologies of TNN. So she was computing this Floer homologies using explicit diagrams and counting some homomorphic disks. If n is large, it's almost impossible, and that's why she had the problem. But using the surgery methods, we can actually compute it.
Excuse me, here you have multivariable, Alexander.
Yes.
So it's not true that for a sublink you just specialize a variable?
If the linking number is non-zero.
Okay. So you need
Yeah.
to link.
I mean, if all linking numbers are zero or non-zero, then that's enough. Yeah.
So before you raise the definition, why is this the right definition? And not, like in the not case, having one L-space surgery?
Because you want right. I want to say yeah. Let's say it now. See. No, so there is a reason why this meta theorem is true, and why we can actually do something with these things is because we have this large surgery theorem, or in general surgery formula. Due to Manifesto, which relates HF hat of 3D to linear Floer homology with a bunch of information with multivariable filtration and so on, where of L inside it S3. And so, in particular, if you know this homology for large surgeries, and that you know, then for large surgery, link surgery formula, this surgery formula is very easy, and so you recover just Floer homology again. Again, some kind of up to some filtration and up to some maybe spectral sequence. So there are some subjects here, but essentially that's how this is proven. And then the question is, in a given example, can we compute the spectral sequence?
So basically the right definition of an L-space not should be something whose sufficiently large surgeries.
That's right, but that's
Which is
which is equivalent to having one voice of
Yeah,
surgery.
yeah.
Why this essentially theorem? That's right, but for links it's better. So there are examples. So Yajin had some examples when you have an isolated L-space surgery. So if some of these conditions are not satisfied, you can have an L-space surgery, but you don't have large L-space surgeries, and so you don't know what to do.
What do you mean by isolated?
I mean, you have some D, which gives an L-space surgery, but you don't have large L-space surgery.
Oh, you mean like,
Or D plus one will like in each direction won't give you an L-space surgery.
okay, so you just mean like,
And you have pair, you have two component things. You have D1 and D2, right? So suppose that like this is not satisfied or something. Then you can have a L-space surgery, but D1 plus 1 and D2 won't give you an L-space surgery. And if you go to large D, then it won't be an L-space surgery. So it could happen.
so isolated in, I mean,
In,
because S3 is
in the space of
so
D's.
somehow, in the,
In the space of D's. So you have
okay.
k-dimensional lattice of possible surgery coefficients. And then you can mark, so I'm getting there right now. So let me see. So you can ask precisely this question, which I will be answering for the rest of the talk. Is that now you have L space link with this definition. And so you can ask, okay, so the question is now which G give space surgery. And for me, again, I want to say that the I are integers. In principle, you can ask about rational surgeries, but they're just more complicated. And so this should be some subset in Z to the K, right? So this is defined as subset LS and L, which is a subset in Z to the K. And you can ask how this set actually looks like. So what do we know about this set? And so what do we know about the set? So again, if we have the L space surgery just says that you have some region far away which is contained. So you have some quadrant somewhere there which is contained in the space L as well. And that's all what you know. So if you have an L space node, it's a reminder. You have L is an L space node. Then LS of L is just the interval onto G of K minus 1. So if you have one single L space surgery, one single positive L space surgery, then you know that everything after that is an L space surgery. And actually everything before but after 2G of K minus 1 is also an L space surgery. And so you have this very nice and sharp bound, which is kind of similar to that bound, and it's well known. And so the question is, what do you have for links? And for links, let me just give you some examples. So example number 1 is that when you have 4, 6 torsions, that's I think the first interesting example. So the set would look like this. Not very good drawing this set. This would look like this. So you have a quadrant. You can say exactly where these boundaries are. So this is something like PQ, and then you shift by 1 somehow. These boundaries you can actually compute in terms of 4 and 6, whatever. This is 6. Yeah. P and Q, that's right. So there are some things, but there is the interesting feature of this thing is that you have an infinite leg going into negative direction, and you have an infinite leg going into negative direction here. And that you can see very clearly, because if you have S3, 6, comma, D on T equals 6, then you can actually compute, or yeah, so that is just reducible, so I think it will be something like L to 1 cross L. So this is, okay. See that this is the same as L S3, 6 on C3. One of the components connects some with L of D minus 6, 1. So if you make a surgery on both components, actually you can use some trick to say that this is the same as surgery on one of the component connects something else, length space. And so it doesn't matter what D is, so for all D, it is contained in this set. So for all D, 6 comma D is contained in this set. And if you think about the argument, the same is true for any cable link of this family that we considered with Gen. So the same, more or less the same shape for small cable links. And strictly speaking, we didn't prove this, but Sarah did, so aside this very recent preprint from Tuesday. So on Tuesday, she just computed this. And not really on Tuesday, but the paper was posted. Alright, so the shape would more or less look like this. And actually, she did much more, so she computed the shape for rational slopes. And then you have some really complicated things going on here. So you have some curve thrown out, and you have some kind of fractal boundary on the side. And that's really subtle. But let me not go into that.
But so technically, that part isn't fractal, it's deterministic, but there are fractal leavings you get for like p equals 1.
Alright, anyway, so I'll address all this. So for integer surgeries, at least you see this infinite line and this infinite line, but the exact shape was computed in this paper. Alright, so this looks weird, and it is weird to me, isn't it? But luckily you can compute some other example. So you can compute an example of an algebraic link, which is corresponds to this singularity. They have two cusps, f(x squared minus y cubed), x cubed minus y squared. So the link contains two links of cusps which are trefoils, and the link number is 4. This gives me two trefoils, and the link number is 4. So you can imagine these trefoils linked like this.
So it's a cable of the Hopf link.
It is the cable of the Hopf link, right? But it's a different cable from that one. So it's kind of two. So that one is like 3/2, 3/2, and this is 3/2 of the third cable. And so you can ask, what's the shape? So which surgeries give you L spaces? And the answer it looks like this. And again, you can compute this boundary and this boundary, but here you probably have something fancy for rational slopes, which I don't know. Right, and so you can ask, okay, so like, what do we know about the shape? Why sometimes you have something like this, and sometimes you have something like this, and what's going on in general? And so, and maybe I should mention to add confusion. So there is a theorem of the same Liu in the same paper, which says that for two components L space links, LS of L is completely determined by the Alexander polynomial. No, and strictly speaking, there was one with Alexander polynomials of components, which you need if the link number is 0, and Alexander polynomial of this link. And it completely determines this thing, but honestly, I have no idea how to look at the Alexander polynomial and get this shape. So there is some algorithm, but it's not so transparent. So for a given D1 and D2, you can decide if it is an L-space surgery or not. But how to describe the set is a complicated question, which I think has not been really answered.
And his results for integer surgeries too.
So for integer surgeries, yes. So I mean, everything what I'm saying is about integer surgeries. For rational, yeah, I'm not completely sure. All right, and so this looks very pessimistic, but that was the starting point for a paper with Andrus. So we proved two results.
Is this known to be false for many?
Huh?
Is this known to be false for many components?
It's not known for many. I would expect it to be false. So again, there is something easy which is completely determined by Alexander polynomials. But this is E2 page of some spectral sequence, and you don't know higher differentials. So for two components, just by some gradient reasons, you don't have higher differential. So that's why this actually worked. And yes, and that you can have higher differential, and I think that's an observation of Liedman that sometimes you do. Maybe again you can look harder and determine them from the Alexander polynomial, but I don't know. Okay, anyway, so theorem 1, which is again some kind of meta theorem, is that for most L-space links, these two components LS of L is bounded from below. And moreover, if D1, D2 is in the set, gives an L-space surgery, then D1, D2 Lincoln number is actually placed. So not only it's bounded from below, but it lives inside some hyperbola. D1, D2 is equal to Lincoln number squared. And I have to explain what most means. So most means, again, some explicit condition on the Alexander polynomial, which I will explain in a second. But if you have a general L-space link, in this condition, you can formulate it quite nicely, but it's still not completely transparent from the Alexander polynomial. For algebraic link, it's completely transparent, and that's theorem number 2. Let me write it here. I should write it here. And so, theorem 2 for algebraic links, the full line equivalent so first of all, LS is bounded from below. And actually more than bounded from below, it satisfies this theorem. One condition. Then you can intersect it with some special lines. Are both bounded. Where M1 and M2 are reducible surgeries. M1 and 2. I'm sorry, L1 and 2. So if you have an algebraic knot, it's always an iterated cable of a torus knot, and so it has a reducible surgery coefficient. So we can take those in 1 and M2. And so it's sufficient to test these two lines. So there is some horizontal line here, and there is a vertical line here. So if it is a cable, then this horizontal line and this vertical line, they're precisely contained in the set. If it's not a cable, you don't know, but if you tested these lines and found that the set is bounded, then it's always bounded. And then the third condition is the most surprising, I would say, is the following. So for the third condition, I want to keep this picture, but I need to correct. Due to, I don't know whom, I guess can be rather there. So maybe it was known before, but it certainly follows from their results that if you have an algebraic link with two components, then all coefficients of the Alexander polynomial are 0, 1. So, yes, I don't know if it was known before them, but it certainly follows from them. And so we can consider the set, let's say support delta, inside of this square is where, so we consider the set of points, the set of exponents of T1 and T2 when the coefficient is 1. And so the third condition in this theorem too is that it is bounded if and only if the support of the Alexander polynomial is not ordered, which is a very easy thing to check. And so what do I mean by this? I mean that if you look at this example, the Alexander polynomial looks like this. So you have T1, T2, and again it depends on your favorite normalization, but it looks like 1. I think you have nothing, 3 point here, 1 point here, so they actually live on the same line. Algebraically it will be 1 plus, I guess, T1 squared, T2 squared, plus T1 cubed, T2 cubed, plus T1 4, T2 4, plus T1 6, T2 6. So they're all on the same line, and they're ordered in the natural partial order on the plane. And so this is not satisfied, and so this is actually unbounded, and this is unbounded. And so in that example, what's the Alexander polynomial? Again, it's really easy to compute, and the Alexander polynomial looks like 1 plus T1 squared T2 cubed, plus T1 cubed T2 squared, plus T1 5 T2 5. And so it looks like this. We have 2 points here, here, and here. It's parallelogram. And so these 2 points are not ordered with respect to natural partial order on T2. And so this set is bounded from below. And then this kind of explains this most in this theorem. So at least for algebraic link, it's kind of generically, you wouldn't expect this support of the Alexander polynomial to be ordered. That's really a really strange condition. And it happens quite rarely, but there are some surprising examples when it happens. And so generically, you would have something like this. For example, if you have 2 curves which are transversal at the origin, you always have some picture like this. If you have some tangency, then you may have some ordering, but yeah. Anyway, it's quite complicated criterion, but so we're quite happy that we can prove it. And also for cables, you always have this situation, so it's always ordered and it's always unbounded. Okay, so now how much time do I have to say something about the proof? When do I end? Yeah,
About 20 minutes.
20 minutes. Okay, cool. So it's more than an hour. I started at 15, right? Okay.
If you want, you can have 18.
Okay.
I can ask you a question.
Yeah, ask me a question before I go.
So do you know where it plunges down? Where this set plunges down? Is it only along the reducible surgery and monotonic?
No, it is thicker than that.
Okay.
So, I mean, I think this is 7 and this is 5 in this case, but it can be, is it 5? No, it's maybe 1 actually, right?
So the one side is PQ plus 1, the
Yes.
other side is PQ minus
Minus B minus Q.
minus P.
So this is 1, right? Okay. So that's fairly thick. So you have this line, and then you go slightly above this line, but you really go below this line.
But it's something like in the neighborhood of that line. Always. I mean, not only in this case, in general. Do you know that? So.
I don't know. Like,
Extreme
I mean, one is
Yeah,
quite
there's
far
always a
from.
neighborhood of the reducibles that you get, because like they're sort of.
At neighborhood, you always get this thing, because, for example, if you have PQ plus 1, then you can still do the same trick, more or less.
You always exclude the lower left quadrant.
Yes, you always exclude the lower left quadrant, that's right. That you can, I think, prove.
So you can't go unbounded in both.
So you can't go unbounded here and here unless it's the Hopf link or something like that.
Yeah. it's like
You
if
can't
use
even go
one,
unbounded
then
here
you can
because-
wrap around infinity and get stuck in the lower quadrant.
So somehow you can't go all the way up and all the way down, so you can't have this half plane, for example, unless one component is unknown. So you have some restrictions, but again, in general, I mean, it's a good question, what's the boundary of this set, for example? I don't know. Even here, I mean, I can compute this thing explicitly because this is, again, a graph manifold, and I can use, for example, Johnson's program to do this. So that's how we found all these answers, but to prove that these things are actually naive-space surgeries, take some job and like case by case, you can do that. So I don't know, it's a very good question, and again, like in light of this theorem, it's completely mysterious. Like, for example, polynomial looks like this and like that, and how do you like look at that example polynomial and see all this complexity from there? That's a very interesting question. All right. So if I have 20 minutes, then I want to explain the proof of this theorem. And then say something about that, because I guess not so many people care about algebraic links. So, but it, okay, so. And also from any point of view, I haven't seen this condition appearing from anywhere, like this, that the Alexander polynomial is ordered. I mean, we asked some people. So if you happen to know someone who knows why Alexander polynomial is ordered, then let me know. Because I mean, there are some very strange examples. Maybe let me say one more example before I go to the proof. So example, okay, can I do it on the spot? So you have a trefoil. Is one component, and another component is it's, oh my goodness, 2 comma yes, surgery 13 is 20. Maybe I'm lying here with numbers, but I'll explain the phenomenon. So you have a trefoil and you have a surgery, and you can arrange so that this is really an algebraic link with these two components. So this, for S at least, yeah, for S odd, I guess, and positive, this is an algebraic link.
You mean it's cable or?
It's a full cable, yes, sorry. So 213 cable of the trefoil is algebraic. And 215 cable of the trefoil is algebraic. And again, you can arrange so that like this is the cable and this is this thing. And so you can ask, okay, this link, is it ordered or not? And it turns out that if S is equal to 1, it's actually ordered, but not on a line. It's kind of close to some line, but you have like, an example polynomial looks like this. You have 2 lines, and then these points are still, this is above this. And if S is bigger than 1, then it's not ordered. So this part will move to the right, and then this stop being ordered. And so this is really a strange condition, I would say. And again, it shows that generically it's not ordered, that's what we would expect. But like what distinguishes this 213 cable of the trefoil from 215 cable of the trefoil, I don't know. I've never seen this. Anyway, right, so now about the proofs. So how to prove many of these things. So, theorem 1. So proof of theorem 1, again, it uses the surgery formula. Monographs conversion. Plus some simplifications due to Floer, so he basically wrote exactly what's going on in the surgery formula for two-component rings. Because in general it was a very, very big complex. Here it's more understandable. So the complex looks like this. So first of all, it will be complex over f of u, where f is equal to 2. And right, so first of all, for each vertex of this lattice, you have a generator. For each middle of edge, you have a generator. And for each center of the face, you also have a generator. And you have tons of differentials which look like this. And it continues forever in all directions. Right? And so all this, at each vertex you have a generator over this f of u. So this means that you have a copy of f of u and you have some map between them which is non-zero. And so the only non-zero map between different copies of f of u is multiplication by some power of u. And so I'm specifically interested in these maps ua, ud, uc, and ud. And again, the content of this theorem of Floer is that you can compute all this a, b, c, d, and all other powers of u, knowing the Alexander polynomial in some way, which I don't want to explain right now. And so then you take total homology of this complex, and this is homology of the surgery. And the only remark here is that what is the size of H1 of the surgery, first of all? So the size of H1 is actually the absolute value of the determinant of the surgery method. Right, so this is some algebraic topology. And now for each class, so classes in here are parameterized by d square mod lambda d square. So homology is naturally identified with the quotient of d squared by the lattice generated by this matrix lambda. And so basically what I need to say is that so here you have some generator z which depends on some point in the lattice. Now this square will actually be shifted by lambda 1. And this square will be shifted by lambda 2. And so this square will be shifted by lambda 1 plus lambda 2. And so on. So you have anyway. Maybe I don't want to go into that. I just want to say some nice thing about homology of this complex. So suppose that you have the giant complex. So the claim, yeah. So if somewhere A, B, C, D are all strictly bigger than 0, so you have some point in this complex where all A, B, C, Ds are bigger than 0, and I want this point to be the center of the face. And S3D of L is an L space, then lambda is positive. Meaning that, so L3D of L is an L space is equivalent to the fact that the total homology of this giant complex is isomorphic to f of u. So this is essentially a equation from homological algebra over f of u. So you have this big complex parameterized by the lattice. And at some point you know that A, B, C, D are positive, and you know that total homology is f of u. Then actually you can prove something about lambda. So how do you prove this?
What does it mean if lambda is greater than 0?
It means that the gradings of generators at the centers are bounded. I'll get there.
Okay, I mean, it's just a definition, so it's a property of lattices that you haven't told us.
No, it is the matrix at positive definite.
Ah, okay.
So this matrix, D1, D2, okay, is positive definite. So the proof is that suppose that we found this point. So suppose that generator in the middle is Z. So you know that differential of Z is U times some alpha. So the differential of Z is divisible by U. So there is some combination of these four guys, which is multiplied by U, and then it is in the image of Z. Now we know then d of alpha is equal to 0 because this is 1 over u of d of c squared, d square of z. And so you have this cycle, and it should be killed by something. So how do you kill this cycle? You can kill this cycle either by z, but it doesn't kill it, or by linear combination of all centers everywhere. And that's the only way you can do this. So we can kill alpha either by z, but that's impossible. Or by the giant sum over all vertices in this z square, or I don't know, z square, z prime, where you have the z prime in the center of all squares not equal to z, maybe times some power of u. And now, because otherwise we will have an extra class in homology, and this would contradict this condition. And now, if you can say this, then this homological degree of this thing is bounded. So this has fixed homological degree. But then, homological degree of z prime are bounded below. Right, because I didn't say this, but the degree of u is minus 2. So if degree of z prime times some power of u is fixed, then the degree of z prime is bounded below by this thing. And on the other hand, homological degrees of the centers are essentially given by quadratic form given by lambda. So these are essentially, how to see? No, let me just write lambda z prime, and you understand what I mean. And so they're bounded below, and then here are. And so it's not negative distance. So it's kind of very coarse argument, I would say, because we didn't really use anything, but I think it's fun. And so you can actually ask about the same argument for one component, and it works perfectly. So you want like one, if you know this complex, so then one of this map, H map and V map should be both non-zero. And if this happens, then this is not a null space. And for one component, it's actually you cannot leave. In general, you need some kind of argument. Okay, so this is some coarse bound, but at least it works. And again, so this condition that I was referring to in the theorem is precisely this condition, that you can find a point where a, b, c, and d are bigger than 0. And you can compute a, b, c, d from the Alexander polynomial, and so and this essentially proves theorem 1.
The theorem is, so the theorem says that for most
For most links, A, B, C, and D are bigger than 0. So generically, you would expect that they're non-zero. All of them. Like for generic L space knot, you would expect that there is a point where both H and V maps are non-zero. That's this condition. For generic L space link, you would expect that, and generically, A, B, C, D are bigger than 0, and then you can run this machine. And so I have 2 minutes to say something about theorem 2, so, and I raised it, so it makes it even more complicated. So just say, so the theorem 2 was that A is LS of bounded, and B is that LS is line is bounded, and C that delta is not ordered. So what do we know? So A to B is obvious. C to A is more or less theorem 1 up to some work relating this ordered condition to this ABCD. And so the interesting part is going from B to C, which says that if it is ordered, so you can formulate it that way around. So if delta E is ordered, then LS, this is one of the lines, is unbounded. And you have to construct an infinite family of L-space surgeries in this case. And do I want to say something about that? Maybe not. Let's stop here.
questions?
Like in this this cable example of the trefoil. So what's going on in criterion B there? So when I take the reducible.
Yeah, so these are precisely these lines which are there. So you take reducible surgery in one component and any other surgery, any surgery coefficient in the second component, and then it will be an L space.
Yeah, what are those manifolds look like?
No, it will be connected sum of surgery in one component with an L space, with length space. So if you have, I think I wrote this. So if you have S3, 6, let's say, and T and T for 6, then this is the same as 6 surgery on one component. Connected sum with length space, I think it will be T minus 6 and 1. So, and then you have many, the same is true, if you have arbitrary number of components, you have reducible surgery in one of them, and then you have,
Right, but so what's different about, the 213 cable versus the 215 cable in terms of
that's an excellent question.
which manifold you get?
You get some graph manifolds, I can show you the graph. Okay, let me say one thing about graph manifolds, which is kind of related to this, but if you don't understand what I'm saying, that's fine. So, secretly for this B2C, we need some statement about graph manifolds. So we have some graphs. This is gamma. So suppose that Phi2 is gamma negative definite graph. And which defines an L space. And then you put some vertex and you want to make a surgery at this vertex. So then for being very positive, gamma D defines an L space. B. So for D less than 0, gamma D defines an L space. If in one D there is a vicious cycle, such that C intersected with I is negative for y, and I are integers, and V is equal to 1. So you have some vertex V, so you compute the cycle in gamma with these conditions. I mean, you look at all cycles satisfying these conditions, and if you're going to find a cycle which is equal to 1 in this case and negatively meet all divisors, then you have large family of surgeries for negative Ds. And that's essentially how we prove this B2C. So we need to find large family of things, and that's exactly what we're going to do. You make reducible surgery in one component, then you're left in fixed negative definite graph, and then you want to know if negative surgeries on that component gives you an L space, right? And so that's exactly what this theorem says. And then it's an interesting question. I mean, the hardest part of this was to relate this criterion to this Alexander-Freiman criterion.
So these ABCDs, you can compute them from the semigroup of the.
Yes. From two-dimensional semigroup of the singularity.
Is it possible that this criterion on delta being ordered works more generally, or do you know examples?
I mean, first of all, you can have negative coefficients. So if you have a general L space link with two components, you can have -1. I don't know.
But like, I mean, is there an example of an L space link where the coefficients of the Alexander polynomial are 1s and 0s, and it's ordered?
And it's not algebraic. I don't know, actually. I mean, another thing which maybe I should say, if you take a Whitehead link, then it's bounded below, and it's like all positive surgeries give you an L space, I think, and nothing else. And that was observed by Yajnik, and you can prove it by this result, because you can find a point where A, B, C, D are bigger than 0. That's really easy. For Robin, I think so, yeah. And for all two bridge links, I think you can do this. So you don't have this plus minus ones, but you can still effectively compute this ABCDs and apply this theorem. And I mean, in some sense, I would say that this ordered condition means that one component is very close to being capable of another. So somehow that's exactly what happens. That you have, like, but I don't know how to quantify this. I don't know what this actually means. So if it is actually capable, it's certainly unordered, or it's certainly ordered. And then if you make it slightly different, but not so different, it's really a mystery. But there are a lot of interesting questions, lots of interesting examples.